Okay, so thank you very much for the invitation to speak in the seminar. It's really a pleasure. Okay, so I'm going to speak on the title is graph potentials and mirrors of moduli space of rank 2 bundles on curves. So this is based on a couple of preprints that I have with Pieter, Belmans and Sergey Galkin. I think maybe towards the beginning of the year or maybe last year sometime, Galkin gave a talk on some aspects. The talk title was something like a combinatorial Torelli theorem or something like that. But again, we are not. So I'm going to keep my talk completely disjoint from that talk. In any case, there's intersection, but there will be some objects that are common. But anyways, okay. So I'm going to talk about the moduli space. So let me just introduce the moduli space. Okay, I'm not sure if you all are familiar with this space. So well, the first example is a example of a threefold, a very popular Fano threefold. Is the intersection of two quadrics in P5. So this is a Fano threefold with pcard number 1. I'm going to call it X22. Okay, and this quadric is actually an example of a bigger class. Intersection of these two quadrics is an example of a bigger class of Fano manifolds. So those are what are called the moduli space of bundles on curves. So I will fix a C of smooth projective curve of genus G at least 2 throughout, and I will fix L a line bundle on the curve, and MC of L will denote the moduli space of semi-stable rank 2 bundles with fixed determinant L. Okay, so I mean, so you all know that if the degree of L and is odd, which is co-prime to the rank, because the rank is 2, then semi-stability and stability coincide, and this gives you a smooth manifold. So if I take L to be of degree odd, I get a smooth thing. But if I take if I take L to be degree even odd, I get a smooth thing. If I take L to be degree even, that's not a smooth thing. Okay, so let me introduce some. Let me just try to familiarize you with this object to some known objects. Okay, in case you don't work on moduli spaces. So as I pointed out, the spaces are isomorphic. And it just depends on the parity of L. So so I'm just going to drop L in the notation, and if the L is of degree even, then I'm going to say plus, and if it's a degree odd, I'm going to say minus. Okay, so one very easy example: if you take L to be the trivial bundle and C is a genus 2 curve, then this moduli space is just P3. Okay, but that's kind of misleading in the following sense. So if I let C be a hyperelliptic curve, then there's a theorem. So this in genus G equal to 2, this is due to Narasimhan, Ramanan, and independently by Newstead. And in arbitrary genus, this is due to Desale and Ramanan, who proved that this moduli space is just intersection of the two quadrics, intersection of two orthogonal Grassmannians. So Q1 and Q2 are two quadrics, and then you look at the orthogonal Grassmannian of G minus 1 planes in 2G plus 2, and then it's just the intersection of those two. Okay, so essentially, if you take G to be 2, this is exactly the previous description, that the intersection of two quadrics in P5. Okay, because right. Okay, so now as I pointed out, this M3 is smooth. Okay, and they're of dimension 3G minus 1, 3 times G minus 1, and they're always Fano. So whether I take plus or minus, these things are always Fano. And the theorem of Dreze and Narasimhan says that the Picard group is Z, and then the index of this moduli space is 2 for the smooth one. So if you take the so the Picard group is always Z, but if you take the index for the other one, the plus one is 4. Okay, so now these are a nice class of Fano varieties. This MC minus, these are all smooth. They are never complete intersections except that one particular case. And then they're also Picard number Z, and they're like far from being toric. Okay, so I'm going to study some mirror symmetry, some versions of those things for this particular Fano manifold. Okay, so let me tell you a little bit more about this Fano manifold. Okay, so if you deform the curve, then this manifold can be deformed, right? If you deform a curve, then the moduli space deforms because bundles on the curves deform. And actually, these are the only deformations. So deformations of these moduli spaces are exactly controlled by the deformations of the underlying curve. Okay. Now, so this moduli space shows up in various different things. It also shows up in these constructions have analogs in geometric representation theory. So if you look at the global sections of these line bundles, of these natural line bundles, because I mentioned that the Picard group is Z. These global sections are known as conformal blocks. Okay, so they have an independent construction using Cas-Moody algebras, and there's a very deep theorems of Bovie, Laszlo, Faltings, Laszlo Zorger, who says that conformal blocks, which are some objects constructed in conformal field theory using affine Cas-Moody Lie algebras, they are actually equal to these functions on this moduli space. So if just imagine that if you have like rank 1 case, so this MC is just like the Jacobian, and then theta is just a theta divisor, so you have like theta function. So this H0 spaces, you can think of this as non-abelian theta functions. Okay, so now the fabulous property of this thing is that as you vary this curve, the moduli spaces vary, but the dimension doesn't change. So for example, if you fix a geometric curve and you change the complex structure, this number will not change. Now the crucial part, which is also important in coming from like the conformal blocks, it tells me that if C is a nodal curve, this can be extended to a vector bundle. So the main problem is that if you have a nodal curve, then there's no good moduli spaces to consider, like which gives you nice things. But here you're saying that okay, I have a geometric object, but ultimately I'm interested in some algebra of functions. I'm just going to ignore that algebra, ignore the moduli, and try to see if that algebra of functions extend. And what is known from this theory is that this conformal blocks, from theory of conformal blocks, that you can continue these deformations to actually a vector bundle on the whole moduli space of curves. Okay, right. Okay, so that's so those are some of the things. Okay, now so I'm going to talk about mirrors. So these conformal blocks play a key role in today's talk, but it will not play a role directly because it will not come up. But everything what is happening, underlying all the results, these conformal blocks and the conformal field theory play a key role. Okay, so let me briefly recall the setup of mirror symmetry, the homological mirror symmetry setup. So we are in the setup of Fano varieties. So X is a Fano variety. The mirror is expected to be what is called an LG model, which is like a quasi-projective variety Y, and W is a proper map, and with some additional properties. And the bigger homological mirror symmetry conjecture says that on the B side you have the derived category of the Fano variety, and that should be equivalent to the Fukaya-Seidel category of the Landau-Ginzburg model. And so that's from A to B, and then also there's B to A, which says that the Fukaya category of the original Fano variety should be equal to the matrix factorization category. Okay, so that's the mirror symmetry. It works like both ways. Like you start with something, and then algebraic geometry of the original thing should be same as the symplectic geometry of the mirror, and then the algebraic geometry of the mirror should be same as the symplectic geometry of the original thing. So it works both ways. Okay, so that's the proposal. This is a conservative version of the homological mirror symmetry. But what you see in both these things common is that if you look at the bottom row, you have this function on the left side. So this matrix factorization category has a natural decomposition in terms of the critical values of this function W, whereas on the other side, the Fukaya category, the quantum cohomology ring, has a natural decomposition in terms of the quantum multiplication by the first Chern class, and those decompositions should coincide because they're the same underlying same category. So same triangular category. So those sets of eigenvalues of the quantum multiplication by the first Chern class should be same as the critical values of the multiplication by critical values of W. So this is going to play. This is like a corollary of the easy corollary of the homological mirror symmetry. But we're going to keep this in mind because this will come up towards the end of the talk. Okay. So, but we are not going to consider the very strong version of mirror symmetry. We're going to consider a much weaker version, which we can call the enumerative mirror symmetry. So which deals with quantum periods. So if you have X to be a smooth Fano variety, then you can take the conservative moduli space of stable mass from a rational curve with k mark points of degree m, and then you can define the descendant Gromov-Witten invariant by evaluating it against the m minus 2th power of the psi class given by the evaluation map, because you have one mark point k equal to 1 here, and then so that defines some number, and then you can compute this expression, this potential function. Okay, one can try to compute this, and the easy version of the let's call this the enumerative mirror symmetry, or like weak Landau-Ginzburg models, is that you're going to have to construct a Laurent polynomial, and such that the coefficients of the constant terms should give you the that gx, the Gromov-Witten, the descendant Gromov-Witten potential, rather the Laplace transform of it. So this is I'm going to call the weak mirror symmetry, or the weak or the enumerative mirror symmetry, and then such a Laurent polynomial W will be called the Landau-Ginzburg potential. And here, as you see, it's like an open part of the Landau-Ginzburg model, because Landau-Ginzburg models are very hard to construct, and I'm not sure if it's even for a Fano 4-fold, these things have been constructed in full generality. I think for Fano 3-fold there are proposals, but I don't think the homological mirror symmetry has been proved completely in Fano 3-fold. I think for Del Pezzo there's a full proof. Okay, so this is the weaker problem I'm going to consider. So for today, so let me do some examples. So again, this I got from AI's the program, for the toric varieties. So if you take x equal to P3, then the Landau-Ginzburg potential is just going to be x plus y plus z over 1 over x y z. And if you take blow up of a line in P3, then the potential is just that. And then if you take like a projective bundle over P2, that's again all these things are toric. And if you know if you see the Newton polytope, so for example, let me write this. So if I take x equal to P2, okay, so then the polytope, the fan polytope here looks like this. So which has minus 1 minus 1, 1 0 and 0 1. So here the potential is just x plus y over 1 plus x y. In particular, what I want you to observe is that if you look at the Newton polytope, so Newton polytope is just the polytope given by the convex hull of the exponents of a Laurent polynomial. If you just look at the Newton polytope, you should get the fan polytope of the toric variety. Okay, so this is the basic observation, and in all these cases, it has been checked that the periods of this Laurent polynomial actually gives you the Gromov-Witten, the generating function for the descendant Gromov-Witten intelligence. Okay, so that's the motivation I'm going towards, so what I said earlier, that those examples are actually theorem due to, I think it's probably first due to Giventhal, saying that if x is a smooth Fano toric, then we can take the W to be the Newton polynomial of the Fan polytope of the toric variety. And similarly, W's are also known for if you have a Fano complete intersection in a toric variety. Okay, so all the examples where this potential has been known is kind of far away from the features of the Fano variety that I'm going to consider today. There is not toric, neither complete intersections. Okay? So for homogeneous spaces, there has been these potentials are known. There's in works of Batirev, Chaukan, Fontaine, Kim, Duco, Van Straten. There's also Bondal and Galkin that computed this for Fano 3-folds, the toric degenerations, and then of course there's this paper of Korti, Galkin, and Kasperczyk where this Gromov-Witten potentials has been the descendant potential has been computed for any Fano 3-fold, and also a lot more. Okay, so today I'm going to compute the weak Landau-Ginzburg mirror, or the Landau-Ginzburg potential for the moduli space of rank 2 bundles on curves. Okay, as I said, this is a Fano variety of dimension 3g minus 3. Okay, so that's the first goal. The second goal is that, okay, so this is a very big dimensional manifold, 3g minus 3. So the Laurent polynomial will involve a lot more variables, and if you want to compute the periods of this Laurent polynomial in the naive way, it's just going, no matter what the answer is going to be pretty horrible to come up with numbers. So what I want to do now is that also tell you how to really give an efficient way to compute these numbers W. Okay, and further, I also want to compute. So remember that I made a statement from, I see one slogan that I gathered from the general homological mirror symmetry conjecture is saying that the critical values of W on the Landau-Ginzburg model side should be related to the multiplication, the eigenvalues of the quantum cohomology. Okay, and then what does this say? What does this sets tell me about the natural decomposition of the derived category of the model of this Fano variety? Okay, so this is roughly the goal of the talk, as I mentioned in the abstract. So let me see how much I can cover. Okay, so yeah, so I'm going to define the potential function of the Laurent polynomial. So for that, I am going to introduce what I called, first of all, I'm going to introduce what we call Trinion potential. So this has appeared as far as you know in the first time in our paper with Galkin and Belmans and Galkin. So what I do is the following. So you take a trinode. So this is an open graph, as you see. So this is like just a node and half edges. So to this trinode, so you can think of this trinode as a geometric object as well. So this is what is called a pair of pans. This thing is called a pair of pans. And pair of pans come with a graph. Okay, and then I have having two kinds of graphs in the sense that the vertices are colored. So one is colored black and one is colored blue. Okay, so if you have a blue colored vertex, you assign this function. Okay, and if you have a black colored vertex, you assign this function. And if you assign a blue colored vertex, you assign this function. Okay, now observe that if I change A to A inverse here, so if I use this transformation A to inverse, this implies that this function will become this plus 1 over ABC plus BA over C plus 1 over ABC. Okay, as you see, if I just take one variable and replace it by A inverse, I get the other function. Okay, and this is also true for the for any other variable, not only A, because the whole function is symmetric. Okay, and if you do it 2 times, then it just go back and forth. Okay, so there's this relation. So this relation is, you can think of it 2 ways. One is like the orientation, taking care of the orientation of the manifold, and also you can think of it as also the fact that the center of SL2 has order 2. So these two things are packaged by this symmetry. Okay? So this is what is called a Trinion potential. Okay, and they are related by the Z mod to symmetry, and I'm going to define define the graph potential for any trivalent graph. So what is a trivalent graph? A trivalent graph is a graph where it's not necessarily a closed graph. It could have like half edges, and if the valency of every vertex is 3. Okay, so these trivalent graphs appear in geometry quite intensely. So one of these trivalent graphs kind of take care of the data of a decomposition of a genus G surface into a pair of pans. Okay, and then trivalent graphs also corresponds to the deepest stratum in the moduli space of curves of genus G with n mark points. So if you take a genus G with n mark points and you degenerate it further, whether every component is rational with 3 mark points, stable rational. So those are, and then you take the dual graph of that curve, you will get trivalent graphs. So they are appearing both in moduli and as well as in this thing. So recall that if I have like a curved graph like this, okay, right? So this is a stable curve of genus 2. So remember, the dual graph of this is you just have components for the number of vertices, and then the edges corresponds to the number of intersections. So you get this graph. This is the corresponding dual graph. Okay, so as you can see, I mean, but this dual graphs also. So if you have this graph, you can also think of it as a different color. You can also think of it like, you know, like you take a pump and blow it up in a balloon. That's what it will correspond to, and then this thing corresponds to this cutting. If you cut them, so then it will get. Get this, and then this is the trinode you have, and this is the trinode you have, and so these are the half edges, and you join them to get. So this is the importance of dual graph in the geometry of curves. So both in the topology and in the geometry. Okay, so using this, I'm going to define a graph potential associated to a colored trivalent graph. So coloring is just an assignment of of blue or black to the vertex set of the graph. And what I'm going to do is that given a trivalent graph, I'm just going to cut all the edges. Okay, so then everything will look like a bunch of trinodes. Okay, and then I just for trinodes I have the Trinion potential and then just add them up. That's the very simple definition. So this is what I'm going to call the graph potential, because it's a potential, is a Laurent polynomial associated to a graph, and here the if it's a closed graph, then it's a Laurent polynomial on the total number of edges in the graph. Okay, so let me do an example, a concrete example. So here is a genus 2 example. So there are two graphs. Okay, so let me do this one. Sorry. So you have this one. Okay. So here, as I say, puncture all the cut all the half edges, cut all the edges. So then it looks like this. Okay. So for the black one, I've assigned. So similarly here, it looks like this, and here looks like this. So for all the black edges, I have assigned. If the vertex is black, then I have this function. Okay, coming from W plus. Okay, so here there are square terms because these things are like equal, right? But this is B, this is A, and this is like A, C, C, and this is W minus. Whereas here it just looks like the old function. Okay, so this is the graph potential. As you see, if you change the graph, okay, the functions are different; they're not same. Okay, so let me do another example. This is a genus 4 graph. As you see, maybe genus 3 graph, I forgot. Yeah. So see there are like 3 black vertices and 1 blue vertex, and so you just write down the function appropriately. Okay, so just puncture at all the points. So puncture. So take your half edges, cut them here, cut them here, cut them here. So then locally it looks like this, like this, like this. So you just add up for all the 4 vertices, and there you will get the graph potential function. Okay, so as you would probably have guessed that the main result of today, that's going to be, I'm going to state it formally later on, is saying that the periods of this graph potential actually compute the descendant Gromov-Witten potential for the original Fano manifold. Okay, so that's going to be the theorem. I'll state it formally later on, but so that's the purpose of the main theorem of today's talk. But so let me tell you a bit more about graph potential, because they are some very interesting. Okay, so yeah, so this is the theorem. So suppose you have a Laurent polynomial in a bunch of variables. So let's say that the x variables are the h variable, like 2 sets of variables. Then you take a mth power, and then you can look at the coefficient of the 0th power, coefficient of where the power of the x's is 0. Okay, so that we are going to denote it by this square bracket w to the power m. And the main theorem that we have, not the main theorem, the first theorem that I want to state is that, though as I showed you in the examples, that if you change the graph, the function changes. But what doesn't change is that the constant term w is the constant term of the powers of the edge variables. So if you look at a open graph and look at construct this graph potential function, and look at the constant term in terms of where the powers of the edge variables are 0, then so it will be a function in terms of the half edge variables. So then it just only depends upon the genus and the total parity of the coloring. So that means that whether the number of blue vertices are odd or even, and whether so that's the theorem. So as you see, this is related. So what I'm saying is that no matter what trivalent graph you take, as long as the genus remains the constant, this produces the same number. So this should remind you of something in the topological field theory, your WDVV equations. So where these diagrams are quite popular. Okay, so if you have this Riemann surface, and if you cut it right here, so that's the corresponding graph that you will get. Whereas the same thing, if you write it like this and you cut it over here, you will get a different pair of pairs decomposition for the same surface. And what somehow I want to say that these two different ways of cutting are the same. Okay, so somehow what we prove is that our constant term doesn't care about these two different ways of cutting. Okay, and there's a theorem of Hatcher and Thruster saying that starting with one pair of pairs decomposition, you can go to any other pair by these moves. Okay, by saying that okay, this cutting is same as equivalent to this cutting. This is what are known as IHX moves or something similar. Okay, but these are also the basis of what are called the WDV equations of associativity. Okay, so that's the first theorem, is saying that the periods don't change as you change the graph. And again, so this can be repackaged into what is known as the Tqft, the topological quantum field theory, is saying that the following: you take a genus G surface with n boundary points, and then you take a pair of pairs decomposition, and to each pair of pairs decomposition you assign this function, and then you contract all the edges by the bilinear form in the Hilbert space, which is like L2 of Z. Then you get a number, or you get an endomorphism on the number of half edge variables or number of punctures, and that is what is called the partition function. And what the theorem, what I stated before, can be repackaged into saying that this defines the topological quantum field theory. Okay, so this is going to be very important. This result is kind of very important in the following sense: that suppose you start with a complicated graph and you want to compute the periods, then you can replace that complicated graph by a very simple graph. Okay, where you can hope to compute the periods very easily. Okay, so here is the result. So there is a formula that I can come up with to compute the periods of the graph potential. Okay, so this formula is just going to be given by that form. So suppose gamma has no half edges. It's like, that means that it's just a graph associated to a compact Riemann surface, a compact surface. Okay, and then you can take what is called the then you can take the following thing. So you can take the necklace graph, which is like this. So you can think of these round shapes as beads, and dot and this. Okay, so as you see, this is the local. So this looks like one bead, right? Okay, it looks like another bead. So you can induct on these beads. Okay, so if you know a formula for one of these beads, that's given by this function. That's given by this function A, which is like a product of some Bessel functions considered as an endomorphism in an appropriate Hilbert space, or Hilbert space of L2 functions on the space of integers, small L2, and then the Tqft theorem is saying that concatenating this open genus genus one surface with two punctures is same as composing these endomorphisms. Okay, and this S just takes care of some signing, that the coloring, and then you get a formula. Then this is the formula that you get. Okay, so you can compute the periods in terms of trace. So this is actually quite fast. I mean, so Pieter Belmans, my collaborator, wrote a computer code to compute these things, and this is actually way faster than by doing it just from definition. Okay, so now a very simple example: in genus 2, you get this thing. Okay, and as I pointed out earlier, that in genus 2, the moduli space MC3. So if G equal to 2, then MC3 is a threefold, an intersection of two quadrics in P5, and for those in the paper of Galkin, Corti, and Golishev Kaspersky, they have computed all those periods, and this thing appears there. Okay, so that's the so this is the first example that where you can actually recover. This is the first hint that the graph potential actually recovers those numbers. Okay, so next I want to do the so that's the so I want to now tell you how we came up with the definition of the graph potentials. Okay, so what we prove is that this the moduli space So recall that the examples that I all gave for toric varieties, this potential is essentially the Newton polynomial of the fan polytope. So one can ask, can this strategy be generalized for other phonomanifolds? Okay, and this is the proposal of Iguchi and Hori. So I'm going to explain a little bit of that towards the end, but the first theorem that we do geometrically to get the graph potential is the following. So we take the moduli space and then we construct a degeneration following Christopher Mannon's earlier work to a toric variety associated to a trivalent graph. Okay, so as I pointed out that if you vary the curve, right? So see, if you have a variety and you want to deform, you have to degenerate the scheme, right? Degenerate the variety, right? It's same as saying that, okay, you take the algebra of ring of sections of that variety and you degenerate that algebra. As long as that algebra is a finitely generated algebra, if you degenerate it and get a finitely generated algebra, you can take the proj, you'll get a family of get a deformation of the original variety. So here, so that's what we do. I try to explain this a bit later on, but let me state the results so that this moduli space MC32 has a natural toric degeneration associated to a trivalent graph. So as I pointed out earlier, trivalent graphs corresponds to degenerating the genus G curve to a maximally degenerate graph with whose all components are rational and the graph is stable. So that corresponds to a trivalent graph, and to that combinatorial data one constructs a toric variety. Okay, and this graph potential is nothing but the Newton polynomial of the toric of that fan polytope of the toric variety. Okay, so there's a toric variety hanging around, and then we prove some results on the singularities, saying that if gamma has no separating edges, that means separating edges means the following: that if you remove that particular edge, the graph becomes disconnected. So in genus 2, those two examples of trivalent graph, they're not. There's only one separating, the one that looks like a dumbbell, but the other one, the one that looks like a theta, is not separating. So if that graph has no separating edges, then we prove that the toric variety that we have is which constructs the degeneration of the moduli space has terminal singularities. Okay, whereas so terminality is a very important property. We will use this property quite a lot. And actually, this is not only for MC minus. This is also true for MC plus. But on the added advantage that one gets by inversion of adjunction is the following: that this MC plus of 2 is in general not a smooth variety. So genus 2 is just P3, but if we just let genus not equal to 2, these are singularities. And what this proves is that what we can prove is that if you have this is a general result of Kawamata, saying that if you have a family of varieties and if the special fiber has terminal singularities, then the generic fiber has terminal singularities. So we recover a result of Kiem and Lee, who proved that this moduli space has terminal singularities by directly working with the Curwan desingularization of this moduli space. Okay, so these are some geometric results. That means that's why I wrote some algebraic geometric results. That's why I said it's the B side. Okay, so now on the A side. So A side is the main theorem which I already hinted at. I'm saying is that if you have a closed graph of genus G with odd parity, then you recover the fact that the periods of the graph potential are exactly the descendant Gromov, the Laplace transform of the generating function for the Gromov-Witten invariant. So that's the main theorem. So you can this should be seen as what is called an enumerative mirror symmetry. And actually one can one can try to actually construct go ahead a bit more. But anyway, so let me not talk about that. So the way this theorem is proved is following the proposal of Iguchi, Hori, and Zhang. So they have a proposal, and I think parts of this proposal for very special cases has been implemented. And then also, of course, there are in dimension 2 Fano varieties, the whole homological mirror symmetry is known. So in particular, this is also known. And for 3/4, this is known by computing both the left hand side and the right hand side and proving that they are equal. Yeah, but I'm going to talk about the general. I'm going to try to execute this Iguchi, Hori, Zhang proposal to prove this theorem. Okay? So let me explain. So when I try to explain the proof, I will come back to this proposal. But let me explain some consequences of this thing. Okay. So so there is a conjecture. Okay, so as you see in the mirror symmetry side, there are two things. So one is saying that the dB of x should be same as fs of yw, and on the other side we say that hook of k should be same as mf of yw, right? Okay, so now both these things. The slogan that I said that the eigenvalues of the quantum multiplication should be same as the critical values, and those control the decompositions of this category. Okay, so we had a conjecture with independently by Narasimhan, who is saying that the bounded derived category of this moduli space should have a semi-orthogonal decomposition as in the following form that I stated. So you should have 2 points, okay, 2 curves, and then go all the way up to symmetric g minus 2, and you end with g minus 1. So in the so if I draw a picture, so let me this picture will not make much sense right now. If I draw like concentric circles like this, you can think of those points sitting here, the curves sitting here. Oh, sorry, not there. Yeah. Curves sitting here, and you are ending with something big in the center. And there's only one thing. There's like a picture you come. So you are like alternatingly you are like coming in concentric circles, like positive and the completely opposite real, and then go one down, then go by the factor of completely complex and then completely real, and then you will converge in the center. Okay, so this is the picture that one has, and I will explain why I drew this picture. And then there are some supporting evidence to this conjecture. The first one was by Kuznetsov and Swarnava, and also by Narasimhan independently, to prove that version of our theorem for r equal to 2, but they didn't have only one copy of the curve. So with Belmans, I added another copy of the curve. Okay, and then this was generalized by Lee and Moon this year for covering. So here I assume that L is of degree 1, but here Lee and Moon prove it for L, arbitrary L of degree coprime to R. Okay, then okay. So now I explain why I drew the diagram. So if you look at the quantum cohomology ring, which again from the big table I showed in the beginning, plays a key role in controlling the Fukaya category of the moduli space. So the quantum cohomology ring has a natural decomposition in terms of the quantum multiplication by this quantum multiplication by the first subclass. Okay, so now this is a linear operator, and then you can look at what are the eigenspaces of this linear operator. This was computed by Munoz quite early, I think around late 90s, I would say. And then he also computed the eigenvalues of these things. Okay, but as you see, the eigenvalues are exactly of the form that I draw in my picture, right? So as you see, this is like negative real, positive real. Then again, the radius goes down by 8. It becomes some positive complex number. So it's going to give a complex number by I, and negative complex, and then again it goes as positive reals, negative reals, and then ultimately it will go in 0. So it will that the same picture shows up here. Okay. Okay. So as I pointed out earlier, in the main slogan of the talk is saying that one of the main slogans is that the eigenvalues of the quantum multiplication should add up with the critical values. So one can ask whether we see these same values as the critical values of the function that we constructed. Okay, so in general, see that in general, so we are only considering some open part of the Landau-Ginzburg model. So in general, we may not get this set completely get all the elements in this set. But some of our functions are so nice that we can, in many cases, we can get the full set. So here is our theorem saying that if you take gamma to be a necklace graph, so again the necklace graph is nice because you can induct on the necklace graph. So we call that the necklace graph is just this graph like this, and this has a very nice inductive structure, and then the corresponding critical sets also has a very nice inductive structure, which we have not completely explored but should be explored. Okay, and also there's like lots and lots of irreducible components. So if you look at the necklace graph and one colored vertex, then you can actually compute the critical sets of this thing to be exactly matches up with the what you get from the eigen multiplication from mu naught. So this agrees with that that observation from mirror symmetry, and that's actually provides support to that conjecture that we had. Okay, so actually the dimensions of the critical sets is also the correct one, because see in Munoz's paper, this thing, so here this eigenvalue corresponds to a point, this which is of dimension 1, this corresponds to a cohomology of a curve, this corresponds to cohomology of a symmetric square, and so on. So as the eigenvalue goes towards 0, the symmetric power increases, as you see in here. So the same happens here, right? So the boundary ones, so the end ones corresponds to most points, and as you go inside, the singularities become bad, and then you get like lots and lots of critical sets. Okay, but the dimension agrees. So this is so this is all in agreement with the mirror symmetry. So this says that our conjecture has some support from the general mirror symmetry conjecture. It agrees with it. Okay, so now let me tell you some recent updates. What has been done in that conjecture, the SOD decomposition. Of course, the first result in this thing was in 95. That was essentially the starting point. That what is the derived category of the intersection of two quadrics, and it looked like point, curve, and a point. Okay, and then Narasimhan and Kuznetsov proved this result, but they said that in the Kuznetsov and Swarnava assumed that the curve is hyperelliptic. Narasimhan did it in general, that the derived category takes the form point, curve, and something complement. And then Lee Narasimhan later proved that if C is not hyperelliptic, you can put in a symmetric square. And very recently, last year, Trivalent and Toric proved that all the components that we conjecture are already there, but they cannot prove that the components, whatever the triangular categories they have, they don't generate the full derived category. So there could be a complement, but our conjecture says that's all. And then after more or less 2 days after this paper was put on the archive, there was another paper by Zhu and Yao, who used techniques from Telemann vanishing theorem, from conformal field theory, and so on, to prove that again that all the components that we conjecture are there, but again they cannot prove that the collection is completely complete. Okay, but then Yao and Zhu and Yao's work actually extends to other principal bundles and some stacks. All right, so this is what is known about the conjecture. So let me pause and let me so this is the whole framework. So we have the derived category decomposition of the conjecture, and then to support that conjecture we have some potentials. That potentials, what we prove is related to the symplectic geometry of the original Fano variety. Okay, because they compute the periods, and the periods actually are the Gromov-Witten descendant Gromov-Witten potentials, and then the critical values of these potentials match up with the eigenvalues of the quantum multiplication. So at least the decomposition is indexed by the same things. Okay, so that they have all the correct numbers. Okay, and then there are also some supporting evidence. Okay, so now I'm going to so the rest of the talk I'm going to talk about what are the steps in proving the theorem. Okay, so the main step is, so like we can think of this general machinery as the Iguchi Hori Zhang proposal. Okay, so what you do is the following: so you start with a Fano variety. So I think the first one, I think this thing was executed for Fano threefolds in Galkin's thesis. Okay, so what you do is that you start with a Fano variety and you construct a degeneration of the Fano variety into a toric variety. Okay, so assume that all the fibers except the special fiber is smooth, and the special fiber has a Kähler form which is torus invariant, and it comes from a Kähler form on the total space. Okay, so now you have a toric variety. So the toric variety is singular because I mean you're degenerating the variety. degenerating the smooth variety, it may be singular. So assume it to be singular. So, but singular toric variety on the smooth part, there is a it gets the structure of an integrable system, and then the moment and the polytope P, which is the dual of the Fan polytope, is actually called the moment polytope, and that's the image of the moment map from the toric variety. Okay, so what one does is that that using that moment map, one takes and then the fibers are all Lagrangian. So one takes chooses a suitable base point U, such that the fiber, the inverse, the torus, the inverse image of that point is actually a torus. It's a Lagrangian torus always, but you choose it carefully so that it's a monotone. Monotone essentially means that it's some positivity condition saying that the Maslov index should be proportional to the volume form essentially. Okay, so so using that toric degeneration, so you have degenerated this thing into you smooth into a toric variety, but you can like symplectically parallel transport, assume avoiding the critical points to move this Lagrangian, this symplectic the integrable system to an integrable system on an open part of the smooth manifold. So in particular, you have a monotone Lagrangian tori in the original variety. So this was done by Nishino, Nohara, Ueda, and also by Harada and Kave. So Harada and Kave works in the more algebraic geometry setup, and this is like more in the analytic setup, or the symplectic geometry setup, the Nishino, Nohara, Ueda. Okay, so now the theorem that we prove is the following, right? So the main theorem that we prove is that if you look at, so then to associate it to a monotone Lagrangian torus, one has something called what is called the Floer potential. So the Floer potential is just the potential that counts the Maslov index to this inside X, or here in particular because we're counting in X0, so inside X that whose boundary lies in the particular Lagrangian that you chose. Okay, but you can define it for any monotone okay, so what we prove is that the Newton polytope of this Floer potential, okay, which is the Laurent polynomial, will be equal to the Newton polytope, will be equal to the Fan polytope of the toric variety. Okay, so in particular, if you know that your toric variety has nice singularities, right? So if you know that your toric variety, the polytope, the Fan polytope, has only vertices as the lattice points and no internal and no non-vertex lattice points, then the Newton polytope is actually the Floer potential of this M0L. Okay, right? So now one knows there's a theorems of Tonkonov, Bondal, and Galkin and Mikhalkin independently, which proves that this Floer potential actually computes the descendant Gromov-Witten invariance. So you can combine all these two results to say that this to check when if you have a potential, okay, the potential given by the Newton polynomial of the Fan polytope of the toric variety, when is that the Gromov-Witten, when is the potential for the descendant Gromov-Witten invariance? So that's one thing. So that's the whole procedure. So that's the whole program. And what we do is that we first construct a toric degeneration. As I said, that in this particular toric degeneration, the conformal blocks play a great role. So this is the toric variety, especially the polytope that I'm going to describe. So the polytope is saying the following. So you have a gamma is a trivalent graph. It's a trivalent graph. Okay. So where E is the set of edges. So I'm going to describe a polytope in here. So okay, E is the number of edges. So yeah, and then so recall that you will have vertices. Locally, the graph looks like X, Y, Z. Okay, and to every vertex you assign this inequality. Okay, and as you see, if you look at this describes the moment polytope, and the moment polytope and the Fan polytope are dual, and just then if you just look at the coefficients of these variables, then you just get the moment. Then you just get the vertices of the fan polytope, and then you just form the Newton polynomial of that. So that's the origin of the vertex potential. The reason that we are able to get a toric variety, and these inequalities are very good significance in representation theory. These are what are called quantum Klebs-Gordon inequalities. So what one does is, as I pointed out, that you look at the section ring, okay, and forget that this section rings has anything to do with this modular spaces, construct it independently using conformal blocks, and then there's a theorem called the factorization theorem, which relates conformal blocks to a nodal curve to conformal blocks on its normalization. So if you have like a maximally degenerate curve, you normalize, you get a bunch of p1s with 3 points, okay, and then you need to study conformal blocks on 3 points, which leads you what is called known as the fusion ring. It's a quotient of the ring of representations of SL2, and then that ring has an explicit presentation. That's exactly the quantum Klebs-Gordon equation that we show that you get earlier. And one shows that this algebra that you get by degeneration is actually a semi-group algebra of a polytope, and that's the polytope that I wrote. So once you have a semi-group algebra of a polytope, it's a toric variety, the pros of that. Okay, so this is how you get the toric degeneration. And finally, we proved this. I stated that I proved this theorem saying that if gamma has no separating edges, this toric variety has terminal singularities. Okay, so we use that result, and then we use that other theorem that I used, saying that in the case of terminal singularities, the Newton polytope of the Floer potential is going to be equal to the Newton polytope of the Newton polytope of the toric variety, which is the fan polytope. And then in this case, the monotone Lagrangian torus is just given by looking at the inverse image of the Barry center, which is 0 in this case, and hence we get it. Hence we get the result that the Floer potential equals the graph potentials that we have if gamma has no non-separating edges. But then if gamma has separating edges, for any gamma, I know that the periods don't change. Okay, so we also get that this result is true for arbitrary gamma because of this Tqft result that I proved. Okay, so then we are done by the Tomkunov, Bondal, Galkin, and Mikhalkin results, saying that this graph potentials actually compute the periods. Okay, so these are the main things that I wanted to talk. So let me end by showing you one table that we computed. Yeah, you can see this table. Sorry, maybe the numbers are too small. So these are the tables that we computed. But as you see, so the top table is for graph potential with odd vertices, and the bottom table is for graph potentials with even vertices. But as you see that, so for example, if I look at this P4, after some time, these numbers become equal. Okay, right? Even for P8, as you see, after some time, right from here, these numbers become equal. Okay, so these numbers are generated by using the formula that I showed. Okay, so if you look at even for P12, these numbers become equal eventually. So if you have like multiples of 4, then there's a pattern here. Okay, actually one proves the following. One proves that if you have g greater than or equal to 2 and k is less than 2g minus 2, then the periods of the odd potential, so then odd equal to even. So this is a mysterious coincidence because we don't know what's the geometric reason for this coincidence. It's just a combinatorial coincidence that we just see from the formulas and then prove it combinatorial. We don't know a geometric proof, but because the varieties themselves look quite different, because one is singular, the singularity is essentially not very nice, but still not terrible. So these Gromov-Witten numbers don't really make sense yet. I don't think so. But while the other hand, we have a nice smooth variety, but somehow there is some behavior, asymptotic behavior, and we don't know what the geometry reason for the behavior is. Okay, so I think I will just end my talk here. Thank you for your attention.